Hey guys, welcome back to my YouTube channel. So in this lecture, we are going to continue our understanding on the diode, the PN junction. So we completely discussed about the PN junction, and today we are going to discuss on the diode current equation. So that is another very important equation that we will be using in plenty of times. So let's see how we are able to get the diode current equation here. So for that, let's take a doping profile of N plus and P. So here it is mentioned as N plus, means it is heavily doped, then P type. So here if you see that is heavily doped, then magnetic area will be much lower than normal. So here you see the normal the distance, that is P N naught, so which is much greater than the heavily doped section, which is NP naught. Okay, so there is a quite difference. So if we need to observe the magnetic charge carrier, the majority charge carrier in this region is the magnetic charge carrier, right? So it will eventually fade to the normal thing. So that is what the observation, it will eventually fade to the normal curve. Okay, so this is the area of change, because these changes because the majority charge carrier from another section will recombine with the majority charge carrier in this section. So then it will eventually fall into a magnetic charge carrier. So this height, this will be called as NP naught dash. This height we call as a PN naught dash. This we already discussed in the injection of light, right? So this is minus XP, this is Xn, this is X is equal to 0. Okay, so here what we can see is the holes will diffuse through this region and electrons will diffuse through this region. Okay, so this is what the doping profile of P in N type, and this is doping profile next step. Okay, so here we are coming to an approximation according to law of junction. So there is one approximation that we are taking. So law of junction, what it's stating is that Pn naught. Okay, so this one, this Pn naught, Pn, the equation of Pn at x is equal to 0, this one, this condition, right? So this can be written as Pn naught e power v by vt. So this is law of junction. So, okay, so n p naught, so n p naught, which can be written as n p naught e power v by vt. Okay, so this is one approximation that we are taking. So I will let you know why we are taking this approximation in the later session. So let me draw another one diagram here. So in the PN junction, how much diagram we are interacting, that much practical idea you guys will be getting. So that's why in every lecture I am focusing mainly on these kind of diagrams and stuffs, so that you guys will be able to understand more things clearly. Okay, so because blindly going to theory and equation won't help us, right? So I will know what are these things is. So this is x is equal to 0, this is xn, this is minus xp. Okay, so the thing is that, so here the current will flow. So what current will flow is that IPN. This is P region, this is N region. So the current is flowing from P to N, that will be represented as IPN net. So this is completely because of drift. Because of external supply, the holes will move from this region to this region. So that profile, first it will be, the holes will be majority charge carrier here, right? So that will be majority charge carrier here. Okay, so in the depletion region it will slowly decrease and it will be constant throughout the depletion region. This is our approximation that we are taking. And then what will happen, that it will eventually become as a minority charge carrier in the another region. So that will be minority charge carrier in another region. So this is we already discussed. So that will be minority charge carrier in this region. So this is what current is, the IPP, IPP of x, the current due to holes that are moving from P region to N region. So here we can state this as IP in N region, N of x. Okay, which is because of diffusion. Okay, so which is because of diffusion. So here this one because of drift, because one majority charge carrier we will consider as a drift and minority charge carrier will consider as a diffusion. That's the key difference. Here the minority charge carrier will keep on increasing and it will be stable in the depletion region up to here, and then it will increase at exponential graph. Okay, so this is the curve where it is IN N of x. Okay, this is electron. Electrons will moving this side, so that current is moving produced in this direction. So this is In P of x, which is because of diffusion, as I said, because it is minority charge carrier. This is drift. Okay, so this is because of drift. Okay, so the net movement of current will be in this direction. So this is the I net. So we are going to find out this I P of n, the current which is flowing from P to n. This is what the current component, which is the current component in forward bias junction, in forward bias PN junction. Okay, so let's the assumption is there. So we are taking some assumptions here. What are the assumptions? The first one, no recombination inside the depletion region. Second thing is the low level injection. I have detailedly explained what is meant by low level injection. The low level injection is the injected magnetic charge carrier will be lesser than the normal, the doping profile concentration. The total current throughout the diode is constant. This is the thing. So IP of n, which is equal to constant throughout the diode. So these three approximation we are taking so that we can calculate the diode equation here. So let me start the derivation now. So this derivation will be important. So in your college examinations also you guys will have. So I net, which is P to n. Okay, so which will be equal to IPN naught plus INP naught. Both is because of diffusion, because these are minority charge carrier. Okay, so if we take this one can be represented as IP of n of x, which is equal to AQ dP. So we are taking the diffusion current equation formula, minus, which is equal to, this is IP of x only, right? So which is equal to minus AQ dP d of x P n of x. Okay, so I think you guys are able to understand this thing. So now IP of n, because of diffusion, which will be, this is because of diffusion, which will be equal to AQ dP d of x. This Pn of x can be written as Pn naught plus Pn naught dash e power minus x by Lp, as it is false. So now this can be even simplified as AQ dP. This one is constant, so differentiation will result in 0. So 0 plus Pn naught dash e power minus x by Lp, and this will be divided by minus 1 by Lp. Okay, so this one can be further written as minus minus will be cancelled. So AQ dP Pn naught dash divided by Lp e power minus x by Lp. Okay, I hope it's understood for up to this level. So let's now take the assumption that Pn naught dash, the difference which will be equal to Pn of 0 minus Pn naught. Okay, so this difference will be the height that they are saying about this one, this height. So this height they are saying from this to this. So this height. So for this height they are subtracting this value minus this value. Okay, so if we doing this, we will be able to get this one. So IPN of x, which will be equal to AQ dP divided by Lp. So they are substituting that one here. So Pn of 0 minus Pn of 0 e power minus x by Lp. Okay, so here let's make another one approximation that we can substitute the law of junction formula here. So from the law of junction formula, if we substitute Pn of 0, which is equal to Pn naught e power V by Vt. So this is one kind of approximation that we took. So AQ dP divided by Lp, if we substitute that here, then that will be Pn naught e power V by Vt minus Pn naught e power minus x by Lp. Okay, so I hope you guys able to understand this thing, right? So this top, which is Pn of 0, this is Pn of subscript 0. So this is Pn naught subscript 0 dash. So these are quite different in the terminologies. So if we take the constant Pn naught as constant outside, then AQ dP divided by LP. If we take Pn naught outside, then the value is e power V by Vt minus 1 e power minus 6 by LP. Okay. So this is the first equation that we are getting. So equation 1, which is the current due to injection of holes from P to N. This is holes from P to N. Holes from P to N. So which is based on injection because of external battery supply. Injection of holes. Okay. So at any distance at x. So this can be represented as P to N x or even P N subscript N. The power holes current in N region because of x. In region N. Okay. So this is the thing. So we know that IP N of 0 that can be represented as, if we substitute x is equal to 0, then dP divided by LP Pn naught e power 0 will be get cancelled, e power V by Vt minus 1. So let's take this as a equation 2. So this is the current due to injection of holes at x is equal to 0. So similarly we can draft the equation for In in P of x. So which will be equal to AQ dn ln np naught e power E by Vt minus 1 e power minus modulus of x divided by ln. So it should be equation 3. So if we substitute x is equal to 0, then I P of 0, which will be equal to AQ ln Pn naught e power V by Vt minus 1. So which is equal to equation number 4. Okay. So now we have to calculate the net current. So net current is a summation of these two. So I net from P to N. So it will be equal to, we need to add equation number 2 and 2 plus 4. So if we summation of both things, let's take common things. So this is common and this is common. We are taking common things from both. So this is common. DPLP is common, not a common. The common thing is e power V by 2. So let me take that outside. So let me have one bracket here and let me take that common term e by V by Vt minus 1. So the remaining thing is that AQ dP by LP Pn naught plus AQ dn by ln np naught. Okay, so this is common. So this term we can represent as I naught. So we can represent the current equation, which is I net, which is equal to I naught e power V by Vt minus 1. So this is our last equation where the I naught, the constant, which will be equal to AQ dP LP P n naught plus AQ dn ln np naught. These subscripts are very important. What this will resemble is the electron concentration. I think you guys already know this. The electron concentration, I have already explained this also. Please go and watch my previous lectures. Electron concentration in P region in equilibrium. Okay. So in question, majority of them the I naught constant that they will give. So this is based upon these things, the area, charge carrier, and these things. It will resemble based upon these things. So this is how the diode current equation can be derived in the things. So I hope it is understood for you guys. So in some cases this can also be written as I naught e power V by eta Vt minus 1. This eta is ideality factor. Ideality factor. So this eta will be equal to 1 for germanium and eta will be equal to 2 for silicon. So this is also very important. Okay, so I hope the diode equation is understood for all of the guys. So which is one of the very important derivation in plenty of college examination these questions can be asked, and also for your examination competitive examination studies also it will be very helpful. So even if you guys have any doubt, please ping in the comment section. This is very simple normal derivation only. I hope it is understood for you guys. So stay tuned for more lectures like this. Thanks guys.